Now I want to do some simulations or some exercise with my tool program Windfc. But before I do this, one example is I want to create step response with the other tool program Csii, and then copy this with a file, with a zim file, into Windfc. So you can see that you can use my identification in Windfc with any data set which should fulfill some form. You need a text file where the points are stored in a special way. I will show you very quickly what Csii can do. Okay. So we go back to the 3PT1 model in Csii. You see I have opened it. That is a model with the 3 time constants 1.5, 0.7, 0.6 and the k which has a size pi. And I want to export now the step response. So I open the step response box, make a recalc, and this is a well-known step response we have used for my inflection point identification. But now I make it a little bit more difficult. I decrease the time. I stop here in this after 5 seconds, and then you get this curve, and you see the final value now is not reached. But you will see in my identification that is enough to identify the parameters. So I now make an export. Here's an export button. The last calculated curve can be exported. Not any curve. If you have more curves, that doesn't work. Just prepared for the last measured curve. So I click on this point, this button, and then the program asks for the name of the curve. That is the step response of 3PT1 with a time scale of 5 seconds. Okay, I store this curve. I open my Explorer to show you this curve. Wait for my Explorer content. If I show you now the Explorer, then you see this curve here is stored as a .sem simulation file, I call it. I have connected this to my notepad, so this is just a text file. If I open this file, you see what happens. This file contains 1 line per point. The first number is the time value. Then there's a separator. In my normal way, the default separator is a blank. And then the step response value comes. So this is the second point, second time value, second step response value. And if you go down with my notepad editor, you see if I reach the last value after 5 seconds, this is the last step response value. So we have here 512 points. That is the standard point number in Csii for a step response. 512 numbers are stored in 512 lines as a text file, and this text file also can be used to read into Excel or any other form, or you can produce curves in Excel, export as a text file, and then can use my identification tool which comes now. Okay, I close Csii and open Windfc. And this identification module is, I see I have a rather old version. Okay, I should take the newest version. Sorry for this moment. Okay, I have just actualized this. The new computer, or my old computer with old versions. Now I have the actual version 7.7.18. Okay, let's start. The chapter 8.2 identification can be found in the identification menu in the first line by time function LS like least square. Yeah, if I open this window, then you see here a box with prepared functions, yeah, starting with step response of a PT1, step response IT1, and so on. So many step responses are prepared, but also other functions like a polynomial function, an exponential function, to a hyperbole function. This is just a list I have worked out in the last years. But of course, if you are a little bit familiar with C# and Windows Forms programming in Visual Studio, it can be very easy to add your personal new function. Okay, depending on which model you have chosen, here you get a list of parameters which are used in this model function. If you want to know which function is behind these buttons, there is a table in my paper which I can open quickly on page 46. We have a table which contains, for example, the PT1. Here's the transfer function, and here's the function which is used. And each function has a plus u offset and offset value. So the measured value can also be horizontally, vertically shifted by an offset voltage. IT1 has these parameters, and if there is a time parameter, note that also a delay is implemented in this program. PT2 with PT2 function, two PT1s, polynomial function. Here you see what you can use is this has nothing to do with step responses, but if you want to have a linear regression, use a polynomial function with two parameters. Then you have a linear regression, or you make a parabolic regression, or I have prepared up to the power of 6, or an exponential function, or two hyperbole functions. Then PID and DT2 step responses are implemented. We use in the lab control system 1. Maybe you can remember this function. So these are prepared, can be changed to any other functions if you are familiar with C#. Okay, let's start with my step response we have created in Rec C#. Here you have an import button. We can import any text file which contains the information of your step response. So if you click on this button, program ask for the file name. I have to look for the file name, so I have to go into my Explorer and load the relevant file I have stored in a folder, which I have to open one time, and after this the folder is stored. Here is the step response of a 3PT1, 5 seconds. That is my file. Now I open it, and the import box has some options. For example, you can change the separator. Default is blank. There could also be more than one curve stored in a text file. Yeah, one time parameter, and then there could follow several function parameters. Then if you have a phase curve, you can activate a phase wrapping or an offset value, ignore the first line if there is a header, or conversion or shifting or anything else. So if you have worked with my zim files, then this is all okay. So I click OK, and you see here my step response curve. So I make the window a little bit more fitting. I can add a fine grid. You see here some grid buttons if you want to have more lines. You see this curve stops at 5 seconds. And now I try to identify this as a step response of what? Yeah, we have to first to check which parameter I want to have. I think I want to show you that I also now can identify the 3-PT1 system with the 2-PT1 curve, similar to that what we have done with the inflection tangent. Yeah, and if I select the model and I go back to the curve and click just on this optimize button. The optimize button is nothing else than starting of my regression method, but note I have not tell you the starting values. Starting values are the fields here. Anytime if I click on optimize, these numbers in these fields are used as starting values. Now we have default values, and I show you if I do nothing for my starting values, the program cannot converge. Yeah, if I click on optimize, you see the program looks for some trials to find a good result, but it can't come to a good result. So you see we need good starting values. So there is a button which helps in finding starting values. Sometimes also this algorithm behind the starting values fails, then you have to do this manually. But many times the initial values could work very good. So here the initial value button uses the inflection tangent method from Reuter. So look for the steepest tangent, think this is a final value, and then make these proposals. And if I now click after this with the starting values of this button on optimize, then you see, okay, this looks really not bad. Here in the beginning there could be an improvement. This comes from the fact that this program automatically adds a delay, but this delay is a critical parameter which is not optimized yet. I start the identification depending on the model with the first parameters optimized, and the parameter box which is not colored is fixed. So you can change this manually, or if you increase the number of parameters which should be identified, click on 5, and then you see all parameters are colored, and now the delay time is also optimized. If I go back to the curve to show the improvement, look here for this region. If I click on optimize now, this should be improved. Is not improved. Okay. Maybe I can help a little bit. Yeah, sometimes I expect an improvement. I make this just manually smaller than the next step after optimization. Yeah. It's not so easy to identify this curve. Oh, sorry for this. Okay, I go back to initial value, optimize again, and now this program doesn't work properly. Oh, sorry, what happens here? I don't know what happens here. Sorry, wait for a moment. Okay, it's a little pity I have started with a very complicated identification of a 3-PT1 step response. I will show you later some more simple cases. Again, I go down to 4 parameters with a fixed delay time. I click on init value and I click on optimize. Then you see the indicator for qualities, the squared sum is 0.7. And this looks rather good. And this curve cannot be optimized. If I add this parameter, the improvement is poor. If I click on optimize, you see this goes down. The example of last moment where I manually changed the delay time gives a larger quality parameters here in the squared sum. So I think this was a identification with using the data of a 3PT1 model, giving now a model with 2 PT1s and a delay time. So far I should store these results, because these results we later want to use for a design of a controller, to check this identification. This looks good, but we don't know if this model is good or poor to define a controller running in a original 3PT1 loop. So I store these numbers for later use. Now I want to show you the possibilities of this program with other models. This is just what we have done is we import a measurement and identify, but you can work with this program in another way. Any of these functions can be tested because here there is a simulation box, a simulation folder which is very similar to this, which can now produce any of these 12 models with a horizontal scaling with a number of points. You can add some noise amplitude, some random noise, and produce now simulated data where you know what is the result, say K2 and time constant 2. We now produce noiseless PT1 step response, and if you click on this button, you see, okay, this is a typical PT1 step response. Now you can check what is with my identification. I click on step response. You see these are the numbers of my last experiment. So if I use these as starting values, maybe this could work, maybe not. So I click on optimize and check what happens. You see this program use the last values from my last experiment as starting values, and the red curve hits exactly over the blue curve, so we can say this is a good identified model. The question is, why is there a difference? Because you see I have here a field which is a delay time which is not optimized, and we have no delay, so there is a manual or delay parameter in the curve, and therefore this is not zero. The exact curve should lead to an exact identification with the least square sum 0. Let's check what happens. You see now this curve goes down. This number here is not really 0, but very small. 1.9 times 10 to the power of minus 0.5 is a rather small number. That is the noise of my accuracy of my numbers. But here you see the original k was 2. Here the result is 1.9 with 5 nines. T1 is also very good, near to 2. This is 0, and this is nearly 0. So this identification throws out good values. Note that I have limited the number of iterative steps to 20, and I have a criterion to stop, which is a tolerance range. So if the change of all parameters are less than the relative change less than 10 to the power of minus 4, then also this identification stops. Okay, now I make this a little bit more difficult. Now I add 500 millivolt noise to my curve. Then you see this 500 millivolt noise is rather large compared with the original curve. So the question is, can I identify with this noisy curve also my system? You see, also if I use the correct values as starting values, that is easy, but now I change starting values manually to 1. What happens with my optimization? You see the curve goes back to K is 1.72 and T1 is 1.84. Near to the original values, different because of course in the noise is rather large. You see this yeah, it's no wonder that there is a difference to my original values, but you can see in spite of noise the system can identify good values. Yeah, you can check this with IT1, with PT2 step response, to PT1 we have done. Maybe this polynomial function identification also can be rather good. Check what I do now. I go to simulation. I show you first without noise. I create now a set of data, 100 points, and my numbers should be just the series 1 to 7. If I now calculate this curve, draw simulated curve, then you see, okay, this is, well, looks like an exponential, it's a parabolic function. The question is, can I identify my original parameters? You see here, I want to start with really 0 values to show you that a polynomial function can be identified without any starting values in 1 or 2 steps. Yeah. If I look for the curve, click on optimize, then you see the resulting parameters here in this list or here in this curve. This was 1, 2, 3, 4, and so on, 5, 6, 7. You see this identification throws out the exact values in one step, gives least square sum, which is very small. So a linear function can be identified in one step. A nonlinear function needs starting values and more than one step. Okay, let's stop here. I think play with this program on your own. Here you see there are some other buttons that are the connections to other modules in my program. I have a interface module for digital scopes. Here you can get the measured scope data, and my adaptive control system also produced data, and here I can use this data also for identification purpose. I think so far maybe I have shown you what you can do with this program. I think the result of my step response of my 3PT1 system should be copied. You see here I have the final point, also the possibility to identify a 3PT1 system with 3 independent time constants. Maybe this works. I reload my curve, so I cannot see this on the second screen. I have just selected my step response measurement. Now I go to 3PT1. I need good starting values, so maybe this initial value point works, doesn't work. It's a good idea to start with a 2PT1 system, take this initial values, the Reuter method, click on 3PT1 and use these methods as starting values. You see the third time constant is 0. 0 is not a good starting value. Let's do this for 0. The offset is also 0. So I make a manual change for this. Let's look for the curve. These are starting values for the curve. Maybe this is good enough to identify the system. You see the starting values are not good. In the results you see this optimization ends now in a local minimum, but now, okay, with typing several times on this button, you see finally, oh yeah, there is a result, but look, K is good, 3.1437 is very near to the original K. T2 is 1.51, original T2, one of the time constants was 1.5. But here you see there is a local minimum where the both other time constants are very identical, yeah, 0.644, 0.644. So looks good, but these time constants are not correct. Yeah, I show you with manual help. Maybe this identification can end up in the correct system. We have no noise. The quality parameter here is 0.046. Let's look if I can force the system. Go to 6.1 and 6.9. I know the correct numbers are 6 and 7, 0.6 and 0.7. Draw the curve. Try to optimize. And you see the program runs always in the same region here. The both time constants are just identical. So the curve doesn't contain enough information to identify the both small time constants correctly. The mathematic is good. If we have three totally different time constants, this works very well. But here you see the curve has not enough information for identification of these parameters. So no, this identification method is limited by noise and limited by complexity of the model. You see the 3PT1 model behind this is a really big nonlinear function with at least 5 parameters. Also, a time delay could be added, but I think that doesn't help much. Okay, so hope you hope that you have worked very good way with this program, and it helps in identification your personal models and processes.